Hello students, in this video we'll discuss quadric surfaces. A quadric surface has the form ax squared plus by squared plus cz squared plus dxy plus exz plus fyz plus gx plus hy plus iz is equal to k. It's a very general expression, so you have linear terms in x, y, and z. So if I just had this part of it, this part of a quadric surface would just correspond to a plane. And then what we do is we add in every possible second order term, x squared, z squared, xy, yz, xz. This is the most general and the simplest extension of a plane to a second order expansion. So we'll look at some very special cases of these quadric surfaces. We're going to look at quadric surfaces of this form, ax squared plus by squared plus cz squared is equal to 1 for various different choices of a, b, and c. So this is a special case of a quadric surface. In fact, every quadric surface can be reduced to something of this form by a translation of the center and by a rotation. So by translation and rotation, I can put every quadric surface into this category. That's not degenerate, we should say. So if we have the special case where all A, B, and C are all positive, then this will generate an ellipsoid, and all cross sections are ellipses. And what these will look like, if all the cross sections are ellipses, you will have a shape that looks like this. All the cross sections will be ellipses, and so you get an egg shape. If two of them are positive and one's negative, so if A and B, for example, were positive, and the C was less than 0, in this case, so 2 positive, 1 negative, you get a hyperboloid of 1 sheet. Okay, so let's do a particular example. If I have x squared plus y squared minus z squared is equal to 1, then what kind of shape will we get? This looks like a smokestack at a nuclear power plant, z, y, and x. So if z is equal to 0, you have the unit circle. That's part of my surface. If z was equal to, say, for example, 1, then you have a slightly bigger circle, circle of radius root 2. Then you get another bigger circle over here. And what you do is you just connect these dots like so. And this will be a hyperboloid of 1 sheet. There's only 1 sheet to this hyperboloid. But unlike the egg, where the egg is pushing out in all directions, the hyperboloid is contracting in one of the directions. So the hyperboloid is contracting rather than pushing out. So that's going to play a notion when we talk about curvature. Now, if, for example, A is greater than 0 and B and C are less than 0, then what we'll get, for example, is we'll get a hyperboloid of 2 sheets. In this case, there's a range where there's a gap. And so what will happen over here, x, y, and z, we'll get a cup over here, put a cup down over here, so we'll have this elliptical shapes, but for only certain values of z. So what will happen is the restriction, for example, if we look at something like this, if we look at, so now there's going to be a range of z where this does not work. So if we look at z squared minus x squared minus y squared is equal to 1, then we see from this that z would be equal to 1 plus x squared plus y squared. And that would say that this point over here would correspond to, in this example, would correspond to 1 or negative 1, because that would tell me that z is plus or minus the square root of 1 plus x squared plus y squared. And so the plus is going to be the top branch, and the minus is going to be the bottom branch. And we see that the absolute smallest that z can be, this is always bigger than or equal to 0, so the absolute smallest that z can be is 1. So the values of z between 1 and negative 1, there's no solution over here. So there's no part of the graph that lies between negative 1 and 1. I get these two sheets so that once x and y become greater than 0, we can start to develop each of the sheets of the hyperbola. These correspond to the case when you have an x squared, a y squared, and a z squared. If one of those is missing and you just have a single variable, either x, y, or z, those will give you paraboloids. Thank you very much.